Take any matrix, multiply it by a vector, and get 0. That sounds like algebra, but it's actually a statement about geometry. It says the vector is perpendicular to every single row of the matrix. Follow that thread, and you'll discover something remarkable. The equation AX equals 0 cleaves all of Rn into exactly 2 perpendicular pieces, with nothing left over. That's our destination, a line and a plane meeting at right angles filling all of R3. Let's see why this always works. Let's slow down and look at what AX equals 0 says, row by row. When you multiply a matrix A by a vector X, each entry of the result is the dot product of one row of A with X. So we can write the product AX as a column vector whose first entry is row 1.x, second entry is row 2.x, and so on, all the way down to row m.x. Setting this equal to the 0 vector means every single one of those dot products must equal 0. So the equation AX equals the 0 vector is really a system of dot product equations. Row 1.x equals 0, row 2.x equals 0, and so on, all the way to row m.x equals 0. Now here's the geometric insight. Each of these equations says that x is perpendicular to that particular row, x is perpendicular to row 1, x is perpendicular to row 2, x is perpendicular to every row of A. Here's a concrete check. Take A equals the matrix with rows 1, 2, 5, and 2, 4, 10. Take x equals the vector -2, 1, 0. Let's compute row 1.x. 1 times -2 plus 2 times 1 plus 5 times 0. That's -2 plus 2 plus 0, which equals 0. Now row 2.x, 2 times -2 plus 4 times 1 plus 10 times 0. That's -4 plus 4 plus 0, which also equals 0. Both dot products vanish, so x is perpendicular to both rows of A. This confirms our earlier general result. When AX equals 0, the vector x must be perpendicular to every row of A. Now here's the crucial step. The null space isn't just perpendicular to the individual rows, it's perpendicular to every vector in the entire row space. Here's why. Any vector v in the row space can be written as a linear combination, c1 times row 1 plus c2 times row 2, and so on, up to cm times row m. Now take the dot product of this combination with a null space vector x and distribute the dot product across the sum. You get c1 times row 1.x plus c2 times row 2.x plus ... plus cm times row m.x, but remember, x is in the null space, so each row i.x equals 0. That means every single term vanishes. We get c1 times 0 plus c2 times 0, and so on, which all adds up to just 0. Therefore, every null space vector is orthogonal to every row space vector. The null space is perpendicular to the entire row space. Let's see this geometrically with a concrete example. Consider the matrix A with rows 1, 2, 5, and 2, 4, 10. Notice that the second row is exactly twice the first row, so the row space is just a line, the span of the single vector 1, 2, 5 in R3. Now, the null space solves the equation x1 plus 2, x2 plus 5x3 equals 0. Since both rows give the same equation, this defines a plane through the origin in R3. Geometrically, a line pierces through a plane at right angles, and together they fill the entire space. We can verify the orthogonality. The direction vector 1, 2, 5 is perpendicular to the plane. Two basis vectors for the null space plane are -2, 1, 0, and -5, 0, 1. You can check these satisfy the equation. For -2, 1, 0, we get -2 plus 2 plus 0, which equals 0. For -5, 0, 1, we get -5 plus 0 plus 5, which also equals 0. So the rank is 1, the nullity is 2, and 1 plus 2 equals 3, the full dimension of R3. The rank nullity theorem checks out perfectly. So the null space is perpendicular to the row space, but we need something stronger. The null space must contain every vector perpendicular to the row space, with none hiding outside. This is the distinction between orthogonal and orthogonal complement. Let's compare these two concepts side by side. Two subspaces are called orthogonal if every vector in one is perpendicular to every vector in the other. That's important, but it only tells us that some perpendicular directions are captured. The orthogonal complement of a subspace V, written V perp, is more demanding. V perp is defined as the set of all vectors perpendicular to V, every perpendicular direction, no exceptions. This is the stronger condition. So here's where we stand. We have already proved that the null space is orthogonal to the row space, but our goal is to show that the null space actually equals the orthogonal complement of the row space, that it captures all perpendicular directions, not just some. To prove this, we need one more ingredient beyond orthogonality, a dimension count. The rank nullity theorem tells us that the dimension of the row space plus the dimension of the null space equals n, the number of columns, that is r plus n minus r equals n. Now, we already proved that these two subspaces are orthogonal. Every vector in the null space is perpendicular to every vector in the row space, and their dimensions sum to the full dimension of Rn. This means there is no room for any perpendicular vector to live outside the null space. Here is the key argument by contradiction. Suppose there existed some vector v that is perpendicular to the row space, but v is not in the null space. Then you could add v to a basis of the null space, creating a set of n minus r plus 1 independent vectors, all perpendicular to the row space. But the maximum number of independent perpendicular directions to an r-dimensional subspace is n minus r. That is a contradiction. Therefore, the null space is the complete orthogonal complement of the row space. As a quick check, consider the matrix A equals 1, 2, 5 in the first row, and the 2, 4, 10 in the second row. The rank is 1, n minus r is 2, and 1 plus 2 equals 3, which equals the number of columns. Everything checks out. A counterexample sharpens this idea. In R3, take two lines through the origin. Line 1 goes along the direction 1, 0, 0, that's the x-axis. Line 2 goes along 0, 1, 0, that's the y-axis. These two lines are perpendicular to each other since their dot product is 0. But their dimensions add up to 1 plus 1, which equals 2, not 3. So the dimension sum falls short of the dimension of R3. Now think about it this way. There's an entire plane of vectors perpendicular to line 1, namely the YZ plane, which has dimension 2. Line 2 sits inside that plane, but it clearly doesn't fill the whole plane. It only captures one of those perpendicular directions. For instance, the z-axis, the direction 0, 0, 1, is perpendicular to line 1, but it lies completely outside line 2. So these two subspaces are orthogonal, yes, but is line 2 the orthogonal complement of line 1? No. And to be a complement, you need the dimensions to add up to n, the dimension of the full space. Here we need 1 plus 2 equals 3, but we only have 1 plus 1 equals 2. Now apply the same logic to A transpose. The rows of A transpose are the columns of A. So the null space of A transpose, called the left null space, is orthogonal to the column space of A. By the same dimension argument, they are orthogonal complements in Rm. Their dimensions add up, r plus m minus r equals m. This gives us the complete picture. The four fundamental subspaces form two orthogonal complement pairs. In Rn, the row space and the null space are orthogonal complements. Their dimensions are r and n minus r, which sum to n. In Rm, the column space and the left null space are orthogonal complements. Their dimensions are r and m minus r, which sum to m. This is part 2 of the fundamental theorem of linear algebra. Here's why this matters. Every vector in Rn splits uniquely into two perpendicular components, one in the row space and one in the null space. We write this as any x in Rn can be expressed as x equals x sub row plus x sub null, where x sub row belongs to the row space X sub null belongs to the null space, and X sub row is perpendicular to X sub null. Now watch what happens when we apply the matrix A. A times X equals A times X sub row plus A times X sub null. But X sub null is in the null space, so A times X sub null equals 0. This simplifies to A times X sub row plus 0, which is just A times X sub row. The null space component vanishes entirely, and only the row space component survives to be mapped into the column space. This orthogonal decomposition is the engine behind many of the most important tools in applied mathematics: least squares regression, the pseudo-inverse, the singular value decomposition, and projection operators. To visualize this, think back to our three-dimensional picture. A generic vector x gets decomposed into its row space component, shown as an arrow along the line, and its null space component, shown as an arrow in the plane, meeting at right angles. So ax equals 0 may look like a simple equation, but it's really a profound statement about how every matrix organizes all of space into perpendicular pieces with nothing left over.